Here's a quiz question. What do you think has the lighting in my corridor, this power button of a power supply, and my DIY overcurrent protection circuit all have in common? If you guessed that they all come with a latch circuit, then you're absolutely right. In a nutshell, a latch circuit is a circuit that turns on or off a switching element and keeps it in that state, depending on a set and reset signal on the inputs that only requires a small voltage pulse to trigger. Now you might be thinking, what is wrong with using the classic mechanical toggle switch, which also often gets utilized for lighting in a room or as power switches in devices? Well, in such cases, there is a bit of a pro and contra situation, about which I will talk about later. But I can tell you for sure that there are plenty of electronic circuits out there for which latch circuits are mandatory, like my overcurrent protection circuit here, that without the latch would just turn on and off rapidly. There are tons of other examples as well, like for example a self-deactivating microcontroller, that therefore draws absolutely no current most of the time. I think you get the idea why I'm so excited about latch circuits. And in this video I will tell you all you need to know about them, so that you will have no problem understanding them and building them. Let's get started. This video is sponsored by Skillshare, which is an online learning community with thousands of useful classes that you can use to level up your skills. No matter if you want to deepen your electronics knowledge, learn a new skill like video editing, or simply want to get edutained, Skillshare most definitely got a fitting class for you. And that is also pretty much why I joined in the first place, because there's always something new to discover and learn. And today I want to recommend to you the class Master Digital Electronics, Logic Gates and Boolean Algebra by Ayachatsuru Mishra, which is a great addition to the digital electronics segment I will cover in today's video. So what are you waiting for? The first 1000 people to use the link in the description will get a 1-month free trial of Skillshare. First off, let's start super basic without even creating our own transistor circuits. For that, let's use this 74LS279 SR latch IC. As you probably already have guessed, the SR stands for set and reset, which are always the inputs of such an IC. The output is usually labeled Q, and sometimes you got a second output, which is just the inverted normal output. So by applying a 1 to the set input, aka a high voltage, the output shoots up to 1 as well, and latches in that state even when the set input goes back to 0. But as soon as reset shoots up to 1, the output obviously gets reset and returns back to 0. As a practical example, I built this circuit up on a breadboard according to this rather simple schematic. And as you can see, the set push button turns the output on and latches it in that state, and the reset push button turns it back off, just like you would expect it. It works this way because such SR latches, in its simplest form, only consist of 2 NOR gates connected together like this. Such a gate, along with others like AND, OR, NOT, and so on, are so-called logic gates. Their inputs and outputs act according to a truth table, like for example with an OR gate, the output will always be a 1 unless both inputs are off, which I think is pretty self-explanatory because it is called an OR gate. But a NOR gate on the other hand is a bit more complicated, because it combines an OR gate with a NOT gate, meaning the original outputs of the OR gates get inverted, and thus we only get a 1 on the output when both inputs are a 0. And like I said before, if we connect 2 NOR gates together and call one input reset and the other set, then we could go through the different input states and find out that this arrangement acts just like an SR latch we had a look at before, because it is one. To practically prove that, I even wired up a NOR gate IC like I just described it. And as you can see, by using 2 push buttons, we once again reach the functionality of a latch circuit. Now, using such dedicated ICs, which also includes the world famous 555 timer that also comes with an integrated SR latch, is all fun and good and pretty educational, but honestly speaking, very few people do that. The reason is that you can pretty much build these same digital logic circuits with just a handful of transistors, resistors and capacitors, which not only cost little to nothing in comparison to the ICs, but they also come with higher current capabilities and you can easily add extra features. So let's try that by firstly recreating the toggle on-off functionality of the Stromstoßrelais, or latching relay as you would say in English, that is used in my corridor for the lights. For that I got myself an extra one, which after wiring it up for tests, can also easily turn on and off a light through the help of one push button input. So let's have a look inside in order to understand how it works and maybe copy some ideas. The only problem was that I quickly realized that this latching relay purely works mechanically, by repeatedly closing an iron core through which a spring is forced through an asymmetrical path to create the two switching positions. Super clever design when you think about it, but not really an electronic solution for power switches in devices that can also toggle on and off. But as it turns out, such a circuit is not really hard to build by yourself on a breadboard. As long as you understand that a P-channel MOSFET is off when its gate voltage is high and on when its gate voltage is low, that NPN BJTs are on if sufficient base current is flowing through them, and that capacitors simply take a bit of time to charge up or discharge. And with those fundamentals in mind, I present you the schematic of this latch circuit, which is pretty easy to understand. The MOSFET here is used to connect the load at the end to the supply voltage, but normally the MOSFET gate is tied to the supply voltage as well, so the MOSFET is off. Only when a push button is pushed, the left BJT activates in order to pull the gate of the MOSFET to ground and thus activate it. At this point, the load turns on and the left BJT latches on, because it is now also connected to the supply voltage. Only problem is that the right BJT is now also active, which without this capacitor here would immediately pull the base of the left BJT to ground and thus turn it off. But since we got the extra capacitor here, which got charged up before, it firstly discharges itself through the right BJT before pulling the left BJT to ground, and thus we got enough time to release the push button. Next time we press it though, the left BJT truly gets pulled to ground, the load turns off, and the crucial capacitor can once again charge up to later repeat this process. Pretty simple and smart concept when you think about it. And as you can see, it works perfectly fine on the breadboards, which is why I invested 30 minutes to build an even nicer looking version of it on a piece of perf board. Now at this point, I want to finally reveal the secrets why you sometimes would want to use such a circuit instead of a simple toggle switch. And the reason is simply that toggle switches are normally more expensive than semiconductor switches. This difference of course becomes more apparent when you go into the high current switching segment. Also, when looking back at the latching relay example, then it is easy to understand that wiring up 3 or more switches on one long corridor to one lamp requires way more cable length and thus money in comparison to just using one additional relay. And that basically concludes the one input latch circuit. But what about a set and reset latch that is not only inside my overcurrent protection circuits, but can also be used for a microcontroller to automatically turn off completely? Well, for that we can use a pretty similar circuit, which is even a bit simpler than before. One set pulse turns on the left BJT, which then turns on the MOSFETs, which then holds the BJT open. And the reset pulse then basically activates the right BJT, which pulls the left one low and thus deactivates everything. And as you can see with my distance sensor that provides the set pulse and my microcontroller for the reset pulse, the microcontroller keeps doing its job when nothing is close, but then turns itself off when something gets close. Now of course, my DIY overcurrent circuit does not work in that exact same way, because it is including relay contacts for the latching. But you should now be able to understand how it works after having a closer look at it. And that was basically the whole point of this video. Since there exists dozens of variations of this latch circuit, which are more or less all just digital logic, which you should now be able to understand a bit better. If I help with that, then consider supporting me through Patreon. As always, don't forget to like, share, subscribe and hit the notification bell. Stay creative, and I will see you next time!